So in example 3, we're asked to find the Fourier series of a square wave. So this is very similar to example 1, except in this example the period is t, whereas in example 1 it was 2 pi. So on the left hand side we're given the definition of the square wave as shown in the green box, and then we're asked to show that the Fourier series is the expression given in the blue box there. And as always, we're going to need the general definition of a Fourier series. This is taken from the lecture notes. This is shown in the red box there. Now, the first thing to notice about this problem is it concerns a function that has odd symmetry. So we can write that f of t is odd. Now, we know from the lecture notes that if we have an odd function, there can be no constant term in the Fourier series and there can be no cosine terms. So this implies that a0 is equal to an is equal to 0. So we don't need to worry about finding the values of a, they're all equal to 0. All we need to do is find the values of the sine coefficients, the b terms. So using the expression in the red box, we can use the result that bn is equal to 2 divided by the period. Now the integral has to be across one period. In this case, we'll choose to go from minus t over 2 to plus t over 2, and then we have the function f of t, and then sine 2n pi little t over big T, like that. Now, because f of t is an odd function, and because the sine function is also odd, the function that we're integrating has an overall even symmetry. So we can rewrite the integral. Instead of the limits minus t over 2 to plus t over 2, we can simply go between 0 and t. To cope with that, we also have to put an extra factor of 2 into the integral. So we can write that bn is equal to 4 over t, the integral between 0 plus t over 2. Over this range, the function has a value a, and then we have sine 2n pi little t over big T dt, like that. Now we can evaluate the integral. We can write this is going to have a value of 4 divided by t. Now it's a sine integral. We can bring the a outside because that's a constant. The sine integral grades up to minus cosine, and there's a factor of minus big T over 2n pi comes out, and then we have cos 2n pi t over big T, and then the limits are 0 and plus t over 2. We can bring out the prefactor here, we can bring that outside the brackets. We can see that the t is going to cancel out. There's also going to be a factor of 2 cancels, so this is going to give me 2a over n pi, and then we can evaluate the upper and lower limit. The upper limit becomes cosine 2n pi over big T, and that's evaluated where little t is t over 2, and then the lower limit is just cos of 0. And also I've forgotten that there's still a factor of minus there. Now we can take care of that minus by switching the order of the two terms inside the brackets. So we can write that bn is equal to 2a over n pi, and then in brackets we're going to have cosine of 0, that's just equal to 1, minus, now if we think about the term inside here, the t's cancel and the 2's cancel, so we're just left with cos n pi, like that. So this is our result for the b coefficients. We're going to have to evaluate these for a number of values of n. So what we'll do is we'll write a table there, n, 1, 2, 3, and then in the second column we'll put down the values of cos n pi. Well, when n is equal to 1 we get cos of pi, that's minus 1. When n equals 2 we get cos of 2 pi, that's plus 1. When n is equal to 3 we get cosine of 3 pi, that's minus 1. So we can see that the cosine function oscillates between minus 1 and plus 1. So if we now think about the term in brackets here, what we can see is that when n is even we get 1 minus 1, so that just gives us 0. So we can write that bn is equal to 0 when n is even. and then when n is odd we get 1 minus minus 1, so the term in brackets has a value of 2, and so we can write that Bn is equal to 4a over n pi when n is odd. So we can now write down an expression, a general expression for the values of Bn. We can write and use those values to write down the expression for the Fourier series. So we can write that f of t now is equal to 4a divided by pi, and then we have our summation, n equals 1 going to infinity, but n can only have an odd value, and we have then a factor of 1 over n, and then sine 2n pi t divided by t, like that. It's often useful to write down the first few terms of the Fourier series, so we'll do that now. We can write that f of t is equal to 4a divided by pi, and then in brackets the first term is when n equals 1, so we have sine 2 pi t over t. The second term is when n equals 3, so we have a factor of 1 over 3, and then sine 6 pi t over t, and then the third term is when n equals 5, so we have 1 over 5 sine 10 pi t over t, and then there'll be an infinite number of terms like that. Now the final part of the question asks us to express the result in slightly different forms. So in the first case we're asked to express it in terms of the fundamental frequency f0. Now we know that if t is the period, that f0 is equal to 1 over t. So we can rewrite the Fourier series as derived above as f of t is equal to 4a divided by pi, and then the first term becomes sine 2 pi f0 t, second term becomes 1 over 3 sine, and then it's 3 times 2 pi f0 t, and then the third term becomes 1 over 5 sine 5 times 2 pi f0 t, and so on. We should perhaps put brackets around those terms like that. We can simplify things a little bit more and get the result underlined in blue by noting that 2 pi f0 is equal to omega naught. So f0 is the fundamental frequency, omega naught is the fundamental angular frequency. So we can also write f of t is equal to 4a divided by pi sine omega naught t plus a third sine 3 omega naught t plus a fifth sine 5 omega naught t, and so on like that. So what we can see is that our Fourier series, in this case of a sine wave, has a term that has the same frequency as the fundamental. It then has a term which has a frequency of 3 times the fundamental frequency, that's the third harmonic, and then it has a term that has a frequency equal to 5 times the fundamental, that's the fifth harmonic.